Alright guys, so here's a short little lecture on capacitors. Um, we left off last time, if you remember, that saying that if we have two parallel plates with a potential across them, then there's going to be an electric field between those two parallel plates, and we can get the strength of the electric field by taking the voltage across those plates divided by the space between them. Now we can use the same idea of having a uniform electric field between two plates, and we can make a device called a capacitor. This is not a flux capacitor. It has nothing to do with Back to the Future or anything like that. In the real world, a capacitor is a device that we use to store electric charge. In a way, it serves the same purpose as a battery, in that you can store electric energy in it and then release it at some later time when you need it. And the way that you put a capacitor in a circuit is you hook it up to some voltage device. The symbol down here is one that we use for a power supply or a potential generator. The longer line, by convention, has a positive potential, whereas the short line is the common or the ground, and is at a lower potential. So you hook it up to this capacitor. Within the capacitor, there's two parallel plates next to each other. Now, a lot of times these will be, kind of flexible metals, and they kind of get rolled, kind of like a cinnamon roll or a jelly roll. And in between the two pieces of metal is something called a dielectric. And this will be some insulating material, so I represent that with this squiggly line here. There'll be a certain distance between the two pieces of metal, and again, you'll hook this up to some potential, and there'll be some voltage across it. Okay, and in that way, what's going to happen is, we will put electrons on this side. This potential generator acts like a pump, so it's going to pump electrons over this side, which will then repel the electrons in this plate and send them back, and then it gets pumped back up, and it's going to keep on doing this until this potential, whatever potential this device is at, until that potential is reached across the capacitor. So if we hook this up to a 9-volt battery, then the potential across these plates will be 9 volts. So if we hook it up to a 1.5 volt battery, this will be 1.5 volts. If we hook it up to 20 volt power supply, this will be 20 volts. You guys get the idea. Okay, so that's what happens. And I want to mention at this point that in the act of putting electrons on here, work is being done. And as we know from our conservation of energy chapter, when we do work on something, we increase the energy. So we are essentially using this to store charge when we use it to store energy. Okay, so there's a property of every capacitor which we call capacitance, and the way we quantify that is we say that the charge on each plate will be proportional. That's what this little sign right here is. The charge on each plate, Q, will be proportional to the voltage across those two plates. So rather than have a proportionality, we like to have a nice equality, so we need some constant of proportionality, and we've kind of done this with other things too. And we'll say that the charge on each plate is going to be equal to something called the capacitance times the potential difference between the plate. Now, once again, this is just the charge on each plate. This is not the combined charge on both plates summed together. Okay, it's just the charge on each plate. One plate will have a positive Q charge, the other plate will have a negative Q total charge. Okay, so the charge on each plate will be equal to the capacitance times the potential difference between the plates. Capacitance, the units of capacitance, are coulombs per volt, which we call the farad. Okay, so it has its own unit, the farad, F. And as I mentioned before, a coulomb is a lot of charge. So very often what we'll see is that the capacitance, rather than being measured in farads, very often will be measured in picofarads or microfarads, okay, or something much smaller. So make sure you guys memorize your pico and micro, and there's lower number prefixes. Okay. So the higher the capacitance, and so we're talking about capacitance again in this slide. The higher the capacitance, the more charge is stored for any given potential. So if you have a 1 farad capacitor, for 1 volt of potential difference, you'll have 1 coulomb of charge placed on each plate. If you have a 1 microfarad capacitor, for 1 volt of charge, you only have 1 microcoulomb placed on each plate. Okay, so the capacitance gives you a number that correlates the charge in each plate with the voltage across them. The higher the capacitance, the more charge you can put on a plate for any given voltage you put across those plates. And as I said, once again, most capacitors, they have a pico or microfarad. It's kind of rare to have a 1 farad capacitor, although we do have one at school, which I have to show you guys. Okay, now you could have air between the two plates. The problem with having air between the two plates is that it's kind of easy for the electric field to become so strong that that ionizes the air, and then the charge will jump from one plate to another plate, okay, which essentially shorts out the capacitor and makes it ineffective in storing charge. So what we'll do is we'll put some insulating material in there, which we call a dielectric. And the effect of putting a dielectric between these two plates is to increase the capacitance. And the way it does this is, if you imagine without any dielectric, we'll have some electric field between those two plates. Okay, with nothing between them, we'll set the electric field. If we do put some insulating material in there, the insulating material itself has molecules in it, and these molecules on the surface can kind of align with the electric field. And what will happen is the electric field always has to originate on a positive charge and terminate on a negative charge. So on the surface of this dielectric, you can kind of see here occasionally what will happen is the electric field will terminate on a molecule on the surface of that dielectric, of that insulating material. So the net effect is that we've reduced the electric field between those two plates. Okay, for the same voltage, the same charge, we've now reduced that electric field. Okay, and that is quantified. The ability of this dielectric to kind of resist the electric field, to lower the electric field, is given a number, and that number is called the dielectric constant. This is supposed to be a kappa. I know it looks like a K. And the way you can calculate kappa is to have the electric field without the dielectric divided by the electric field between the plates with the dielectric. Okay, so that's all it does. Again, what this insulating material does is it lowers that electric field, and it'll allow you to get more charge on that capacitor. Okay. Alright, so what it comes down to is that the capacitance of a capacitor will depend on three things. The area of the plates, the more area that you have, the greater the capacitance will be. The dielectric constant, so the more effective that dielectric is in resisting the electric field or reducing the electric field, the more charge you can get on for any given voltage. And then the distance between the plates. Okay, and it turns out that we can express the relationship between charge and voltage and capacitance with this equation as well. And this, in the parentheses here, this equation gives you capacitance. So once again, the capacitance will increase with greater dielectric constant, which again means that you get more charge on each plate for a given voltage. This is a constant universe. This is a permittivity of free space. The area of the plates, the larger the area of the plates, again, the more charge you can get on for any given voltage. And then the distance between them. Okay, the lower that distance is, the more charge that you can get on for any given voltage. Okay, so capacitance is inversely proportional to distance, but directly proportional to area and this dielectric constant. Okay. Now, as I was saying, as the capacitor is charged, energy is being stored in it because work is done in charging it. The work done, you have to do work in putting the electrons on here. And because you're doing work on that, you're increasing the energy of the system. Okay. There's various ways that we can calculate the energy stored in a capacitor. They're all equivalent to each other. But the energy stored, you could say it's 1/2 the total charge on each plate squared divided by the capacitance. Or it's 1/2 the capacitance times the potential difference between the plates squared, or it's 1/2 the charge on each plate times the potential difference between them. Any one of these three will work. It'll tell you how many joules are stored in a capacitor, and depending on what the problem is, you can decide which one that you want to use. Okay, so here's a problem for you, and I will let you pause the video and you can see if you can solve it. And then I will go through the answer with you. Alright, so The first thing that we need to do is, if we're told that we need a 75-watt light bulb, we need to know how much total energy is needed to power a 75-watt light bulb for 1 minute. Power, you remember, tells you energy per time. So what this light bulb does is it uses 75 joules of energy every second. And if we're going to run it for a minute, that'll be for 60 seconds. So we need a total amount of energy of 4,500 joules. Okay, and so that's what we're doing with this calculation here. Then we'll calculate the potential difference between the plates, since that's what we're asked to find. And we're going to use this equation. We know what the capacitance is. We want to find what the voltage is, and we just found out what the energy is. So this equation, will let us find what we need to find. And then you solve for potential, and you get 52 volts. Okay, so if you put 52 volts across the 3.3 farad capacitor and charge it up completely, assuming that, again, the insulating material doesn't break down, which, by the way, can happen if the charge gets to be too much. You can actually punch holes through the insulating material and you have the capacitor break down on you. But assuming none of that happens, we can, it has a tolerance up to, above 52 volts, you can apply this and you could power that 75-watt light bulb for 1 minute. Alright, so that's what you guys need to know about capacitors. If you have any questions, let me know.